Chapter number 5, magnetism and matter. See, in introduction, some history related to the discovery of magnetism that is given to you. In Greece, there is one island named as Magnesia. There the shepherds observed this thing, the nails in their shoes stuck with the ground. So when they carried out study related to this phenomena, then came to know about the characteristic which do this thing. And it was observed at the island named Magnesia, so termed as magnetism. Then after so many studies were carried out related to it, then in those days, people developed magnets and they observe this thing. If magnet is suspended freely, then it always align in geographic north-south direction of the earth. So then after they came to know about this thing, earth also have its own magnetic field. And in those days, they used magnetic needles for the navigation. But now the important thing, that is some of the commonly known ideas regarding magnetism. Okay. And now this we have to discuss first. Okay. Now see, the earth have its own magnetic field. So we can say earth itself behave as a magnet, and earth's magnetic field, that is from geographic south to geographic north. Okay. Then after, second thing, if a bar magnet is suspended freely, then we can observe this thing, it aligns always in north-south direction. And the end of the bar magnet, which one is towards the geographic north, that is called north pole of the magnet. And the end of the magnet, which one is towards the geographic south of earth, that is known as south pole of the magnet. So each magnet have two poles named as north pole and south pole. Okay. And experimentally we can observe this thing between like poles. It implies that between north and south. So between like poles, repulsive force is there, and between unlike poles, means between north and south, there is the attractive force. Then monopole does not exist in the nature. Monopole does not exist in the nature means what? See, if we think about any magnet, then two poles are there. One that is north pole, another one that is south pole. So independent north pole or independent south pole is not available in the nature. This magnet that we term as magnetic dipole. In electrostatics, we studied about electric dipole. One charge is positive, another one is negative, right? Equal in magnitude, but with opposite characteristic. Exactly like that here. North pole, south pole, opposite characteristic, but are equal in magnitude, and magnitude of the pole is represented by term pole strength. Later on, we will discuss this thing. Okay. So in electrostatics, we have independent single charge, either positive or negative single charge is available. But in magnetism, monopole does not exist. If we have a bar magnet and if we break up it in two pieces. Then we will get two independent magnets, but somewhat weaker properties. But we will never get the single pole. Then it is possible to make magnets out of iron and its alloys. So these are some facts related to the magnetism. Clear to all of you? The bar magnet and the magnetic field lines. See, if we have a bar magnet and if we sprinkle the iron fillings in the surrounding of it, then the arrangement of that iron filling in the surrounding of it will give you the magnetic field lines. Means, as per the arrangement of that iron fillings, you can prepare the magnetic field lines of that particular bar magnet. And here we can observe this thing, the magnetic field lines always form a closed loop. And if we draw the magnetic field lines by using these iron fillings or using magnetic needle, then we can observe this thing for the bar magnet and for salt solenoid. The magnetic field lines are identical. Field lines form a closed loop for the bar magnet. It comes out from the North Pole and outside the magnet, it reaches to the South Pole. And inside the bar magnet, it is from south to north. In that way, it forms a closed loop. See, bar magnet, that is the magnetic dipole. So solenoid, that also we can consider as a magnetic dipole, because when current is passed through the solenoid and it produces the magnetic field identical to the magnetic field of bar magnet, means definitely one end of the solenoid that behave as north pole, other end of the solenoid behave as a south pole. But here if we think about electric dipole, then we know this thing. Electric field lines never form a closed loop. Electric field line comes out from the positive charge and end up at negative charge. Again, it will not move from negative to positive. So it will never form a closed loop. Clear? Then, if we draw the tangent at any point on the field line, then that will give you the direction of the magnetic field exactly at that particular point. Here in figure, you can observe the magnetic field lines and electric field lines for bar magnet and electric dipole respectively. Clear? Then, if the number of field lines passing through any surface area consider at a particular point that is more, then we can say in that particular area or at that point, the magnitude of the field that is more, or we can say the magnetic field is stronger one at that particular position. And if we consider the number of field lines passing through any particular area considered at a point, which one is very less, then we can say at that point the magnetic field strength that is weak one. So number of field lines passing through unit area normal to it at any point will give you the magnetic field intensity at that particular point. Then we can say two magnetic field lines will never intersect each other, because if two magnetic field lines intersect each other, then at the point of intersection, you can prepare two tangents. It implies that at the point of intersection, two directions of the magnetic field will be there, which is never possible. Any vector never have two directions at any point. So in general, we can say two magnetic field lines will never intersect each other. That the same thing we discussed for the electric field lines also. Clear to all of you up to this one? Now, bar magnet as an equivalent solenoid. So here, let's derive the equation for the magnetic field at any point on the axis of the solenoid, the point that is outside the solenoid, and then here we will represent that particular equation in terms of magnetic moment. And we will see this thing, that equation is exactly like the equation of the magnetic field of bar magnet on its axis. Or in other words, we can say from that particular equation, we can prepare the equation for the magnetic field at any point on the axis of the bar magnet, as well as at any point on the equator of the bar magnet. Now see, as shown in the figure, we have a solenoid having total length that is 2L. So from the center of the solenoid, either side, we can take the length that is LL. Radius of the solenoid is A. Now on the axis of the solenoid, consider a point P, which one is at a distance R from the center of the solenoid, and R is greater than L. Okay. Now at point P, we want to find the magnetic field. Okay. Now see here. We know in previous chapter, we derived the equation for the magnetic field at any point on the axis of the current carrying ring having n number of turns. That is mu0 n I r square upon 2 into x square plus r square raised to 3 by 2. So here we can consider the concept like this. If we consider the solenoid is made by this type of so many thin rings from one end to other end. And for each ring, if we take the magnetic field at point P, and then after if we take the summation of all those, we will get the resultant magnetic field at point P. So for that, first consider one infinitesimal thin ring on the solenoid having length of the ring equal to dx, which one is situated at a distance x from the center of the solenoid. Clear to all of you up to this? Now, first of all, we have to take the magnetic field at point P due to this particular ring. Now see here. Suppose the number of turns per unit length of the solenoid, that is small n. Now number of turns per unit length in the solenoid, that is small n, then the total number of turns in this particular ring having length equal to dx is how much? So number of turns in the ring, that is capital N, that is n dx. Now, with respect to this ring, point P, that will be at a distance r minus x. So, Here now we can write the equation of the magnetic field at point P due to this ring. As per this equation, dB equal to mu 0, total number of turns in that ring, that is N dx, current I, radius of the ring, that is equal to radius of the solenoid, that is A square, into 2, then the distance of the point from the center of the ring, that is R minus X, square of it, plus square of the radius of the ring, so that is A square, and whole raised to 3 by 2. So from this particular equation, we prepared the equation for the magnetic field at point P due to this ring, which one is under consideration. Clear to all of you? If we consider the solenoid is made by this type of large number of thin rings, starting from one end to other one, and due to each one, if we calculate the magnetic field at point P, and then after if we take the summation, we will get the resultant one. So for that, now we can use integration. If this particular integration, this equation is integrated from one end of the solenoid to other end of the solenoid, then we will get the resultant magnetic field. So resultant magnetic field at point P, that is equal to integration dB, and the limits are minus L to plus L. From the center is taken as 0. One end that is at plus L, other end that is at minus L. Now mu 0 n I is square by 2, that is constant, so it is taken outside the integration. So integration minus L to plus L dx upon R minus X whole square plus A square raised to 3 by 2. Now here, consider R is very much greater than X, as well as R is very much greater than A. So in that particular case, in this bracket R minus X, you can neglect X. Then compared to R square plus A square, you can neglect A square also. So resultantly, this denominator, that will be R square raised to 3 by 2, means you will get R cube, that is constant one, so again taken outside the integration. So now mu 0 n I A square upon 2R cube integration minus L to plus L dx. So integration dx, that is X, limits minus L to plus L. This part, that is as it is. Now substitute the limits. So X equal to plus L, then minus X equal to minus L. So B, that is mu 0 ni A square upon 2R cube into 2L. Now we want this equation in terms of magnetic moment. Now see, as per definition, we can write magnetic moment, that is NIA, means total number of turns, I that is current, and A that is area of the loop. Now here, total number of turns in the solenoid. So small n, that is the number of turns per unit length. Total length of the solenoid is 2L. So n into 2L will give you the total number of turns in the solenoid. Then current passed, that is I. Cross-sectional area, that is pi A square. Now we want to introduce this m in this equation. So see, n, 2L, I are there. So to take area pi A square, here multiply and divide this equation by pi. So B, mu 0, n into 2L. So this n and 2L are taken together in this bracket. then current I, then multiply a square by pi, so pi a square. So here divide by pi also, so 2 pi r cube. Now see, n into 12 into I into pi a square, that you can represent as magnetic moment of the solenoid. So B, that is mu 0 into m upon 2 pi r cube. Now multiply and divide by 2. So you will get magnetic field at point P, that is mu 0 upon 4 pi 2m upon r cube. So from this one easily you can write, if on the axis that is mu 0 upon 4 pi 2m upon r cube, then on the equator you can write the equation mu 0 upon 4 pi m upon r cube. Clear to all of you?